Right? We start with Kirchhoff's law, page 242. This one summarized for you. You should be able to solve all this type of problem lah. There's a syllabus. Right? There's the elementary charge. There's your resistor in series and resistor in parallel formula given in the formula sheet. Right? This is a simple circuit. You got a source of energy or battery. Then got a resistor. This is a light bulb lah. And a switch. That's a simple circuit. Then we can have a network. Can have more complicated one. 2 lamp, 2 resistors in series, 2 resistors in parallel. Right? More complicated network. These are the old symbol for resistor. This is the new one. Right? They are different type of resistor, but in practical, you will encounter this one lah. Sometimes this type lah. For paper 3, usually you will use nichrome wire lah, because it has a higher resistance. But this type of resistor is cheaper lah. Okay, row of resistors provide a path or divert the flow of current to reduce the size of current to the desired value. There's a resistor, O symbol. Kirchhoff's second law, right? That's my abbreviation, Kirchhoff's voltage law. Kirchhoff's voltage law. In a closed loop, the total EMF equals the total PD drop across the component. So for the equation form, one side is the total EMF, and this is the PD drop across the component. Right? This is the voltage source. This is the PD drop. Or we summarize it as total EMF equals the total PD. Kirchhoff's second law is a statement of conservation of energy. Memorize. Kirchhoff's second law is known as the voltage law. Voltage law gives a relationship between voltage drop around any closed loop in a circuit and the voltage sources in that circuit in the loop. The total of these two quantities is always equal. Right? We will derive a resistor in series in a while. Right? That's your source of energy, V. So we will derive V equals to V1 plus V2 plus V3. Note, right? There's a symbol form, sum of EMF, sum of PD, or V equals to V1 plus V2 plus V3. Where the symbol, that symbol is a Greek letter sigma, meaning sum of. Kirchhoff's voltage law can be applied to only closed loop. So what is a closed loop? A closed loop must meet two conditions. First condition, it must have one or more voltage source. This is not a closed loop, no voltage source. This is a closed loop, there's a voltage source. Right? That's a closed loop. Right? It's not a closed loop, no voltage source. Second condition, it must have a complete path for current to flow from any point around the loop and back to that point. It's not a closed loop. Right? The current cannot flow anywhere, cannot come back again. It's not a closed loop, current cannot flow. Second law is a law that summarizes conservation of energy. Okay, let's go to derive resistor in series. Their equation, R total is R1 plus R2 plus R3. We're interested in 3 resistors in series. there's the voltage source, there's the ammeter, there's the voltmeter. We assume that ammeter, no resistance, ideal ammeter, ideal voltmeter. A cell of EMF supply current to 3 resistors. Right? That cell has no internal resistance. Assume negligible internal resistance of the cell. Current through each resistor is the same. That's a key to remember. Series, the current through R1, R2, R3 is the same. Conservation of energy. Right? That's by conservation of energy. Energy supply, that's your energy source. Energy dissipated in the resistors. Right? So you can think it of rate of energy supply, rate of energy dissipated. V times I, V1 times I1, VI times I2, VI times I3. Cancel the I, we get, there's a Kirchhoff's voltage law, simplified form. Right? We want to represent that resistor with a resultant resistor. Right? Same voltage source, same current flowing through the circuit, but the total resistance to replace is 3. RT total, R for total, RT for total. Can replace the 3 resistors in series in the circuit with a combined resistor, RT. The same battery, the same current flow through the circuit. Right? We call it combined resistors, this one, of total resistance or resultant resistance, equivalent resistance, depending on the book you use. Right? We have already derived this equation, Kirchhoff's voltage law. PD across each resistor is proportional to the magnitude of the resistance. Yes, PD is proportional to Ri. That means if R1 is the largest resistance, then the potential difference across R1 is the largest. So as Vi equals to IRI, right? I is constant, then we can replace this one, this one, I times R1, sorry, RT times I, then this one, I times R1, I times R2, I times R3 from this formula. Cancel the I, we get our equation. Any comment? Anything not clear?
Oh, so far no.
Okay. For identical resistor in series, it's all of them the same value. For n resistors, each of resistance R, total resistance is NR. What's the resultant resistance? Okay, try this one for me. What's the total? This is a simplified one. Your SPMO. What's the value? Yep. What's the total resistance? Ah,
6.5.
okay, good. 6.5 kilo ohm. Kirchhoff's first law. Right, we have Kirchhoff's second law. Now we go to Kirchhoff's first law. Right, there's your voltage source. There's your light bulb. Current I2, I1 going out, I4 going out, I3 going in. Kirchhoff's current law, the sum of current entering any junction is equal to the sum of current leaving the junction. Or another way of saying is the sum of current equals 0. Right? So in this case, example, I1, I2 is leaving, I1 plus I4, I2 and I3 is going in, I2 plus I3. That's Kirchhoff's current law. It's the statement of conservation of charge. That means total charge entering this junction equals to total charge leaving the junction. Right? Kirchhoff's current law applies to a junction point. Right? Or I call it KCL, Kirchhoff's current law. Another way of writing it is to say that the sum of current entering equals to sum of current leaving out, or sum of current equals 0. That means we have to decide lah. Going in is positive, going out is negative. So you positive subtract the negative current equals to 0 lah. Taking going in at positive and going out at negative. Okay, resistors in parallel. Right? That's your cell, voltage source. There's your resistors in parallel. So we are going to derive this equation. Right? There's another way of drawing this thing. Same thing. Okay. Here's your branch. One branch. Then we are going to replace the 3 resistors with a resistor. Same battery, same current. Right? First, we are going to look at the current, that junction there. That junction there. Right? Which is that junction there. That junction there. Where we go to I1, I3, I2, I1, I3, I2, I1. Here we want to determine the combined resistance. And the combined resistance replace the 3 resistors in parallel. The cell provides the same current. Okay, here the resistance in parallel. We want to find same battery, same source of energy, same current flowing through, but replace it with a resistance, a combined resistance. Replace it 3 with 1. Right? The cell of EMF V, negligible internal resistance, supply a current to the 3 resistors. PD across each resistor is the same. That's how we know it's parallel. The PD across each resistor is the same. I1, I2, I3. So I, current going into the junction, going out, I1, I2, I3. Then replace your I with V, Ri. Right? V divided by I1. Sorry, V divided by R1. Right? This one is from here. V divided by RT. That's for this current. Right? I1 is just your V divided by R1. I2 is V divided by R2. I3, this branch, is V divided by R3. We cancel the V off, we get our answer. Any comments so far?
Uh, 1 over R is like, it's a C, wait, parallel circuit, right? Like
Parallel
the
circuit,
arrangement.
the PD across each resistor is the same, no? V. So you want to find I1, it's just V divided by R1, no? I2 is V divided by
Oh,
R.
because it's parallel.
Parallel.
Okay.
Right? Here we apply Kirchhoff's current law, this part. So for resistors in parallel, the effective resistance or combined resistance is always smaller than the smallest resistance in the circuit. Right? It means that RT is always less than the smallest value in this R1, R2, R3. It means when you combine the resistance in parallel, it's always smaller, smaller than the smallest one. For N resistors for N identical resistors in parallel, each of resistance R, the effective resistance is just divided by N, no? R divided by N. Right? As I say, there are other terms used: combined resistance, equivalent resistance, effective resistance, total resistance. For two resistors in series, you can use a product. The top is the product, bottom is the sum. Right? Or you can prefer to use this one. Right? If you can use this one, it's faster. Right? It doesn't matter. If you don't want, you can use the original formula. Okay, what's the answer for this one? Two resistors in parallel. What's the resultant resistance of the two resistors, 10 ohm and 20 ohm? What's the answer?
3 over 20. Wait, what?
30, 10 times 20, 10 plus 20, 6.6, 6.7 ohm lah. Okay, not? Yep.
So isn't it just 1/10 plus 1/20?
1 over 10 plus 1 over 20. Then after that, you add it up already, you have to invert it, right?
Or meaning become 20/3.
1 over 20 plus 1 over 10. Then after that, you have to invert it, right? Because you are using the original formula, right? You're using this formula, right? You have to invert this one to get RT, right? Okay, now, okay, now. I'm using this
Oh
formula.
yeah, I got it already. Yeah, got it.
Okay, effect of voltmeter. Right? This is 300 volt battery. This is 1000 ohm, 1000 ohm. Ideal voltmeter. Then each one you should be able to do mentally. This is 100 volt. This is 300 volt, 200 volt. Right? But usually our voltmeter has internal resistance. Right? The one in the left one, the analog one, is about 2000 ohm. So we can see what is going to happen. Right? This 2000 becomes 1000. No? So this 150. What is happening? Right? Ideal voltmeter measure the correct voltage. But if there is a voltmeter got resistance quite similar to that resistor, it's going to change the voltmeter reading, change the voltage reading across a 2000 ohm and a 1000 ohm. Right? Another way of saying is the voltmeter draws current, thus give a wrong value, systematic error. Can any comment? Anything not clear? Okay, a voltmeter has a resistance. There's a voltmeter has a resistance R2. It's used to measure the PD across a load of R1. Thus, the effective resistance is no longer R1. Right? When you have a voltmeter, you change the resistance value to parallel resistance or effective resistance. Consider the effect of R2 on R1. Right? You give R1, R2, they are the same value, 100. Effective is 50 ohm. We increase R2 higher, 10 times higher than R1. You get 90.9. What do you get for this one, the next one? If we increase it to 100 times larger than R1, what is RP? Calculate and see what is your value. Yeah, just using this formula. What do you get?
I got 99.
Okay, quite close to 100. Quite close to 100. Okay. How about this one? 100,000 ohm. What do you get?
I got, oh, this one is 99.9, yeah.
99.9. Right? You can see that if it's a thousand times, R2 is a thousand times higher, the resistance of the voltmeter is a thousand times higher than this, the resistance we are going to measure. Then the effective resistance, it doesn't change much, right? You can see 99.9. Okay, that's the advantage of having a high resistance voltmeter to measure R1, the voltage across R1. Okay, when R2, resistance of voltmeter, is greater than the resistance you want to measure, R1, is about 1,000 times larger than effective resistance, then we can say that R1 equals to almost equals to effective resistance. So RP equals R1 when R2 is very much greater than R1. Okay, so important when you want to measure the voltage across R1, the resistance of voltmeter must be about 1,000 times greater than R1. The voltmeter of high resistance measures PD across the resistor without changing it. Right? Or another way of saying is the current draw by the voltmeter is negligible lah. Okay, let us try some question. How about this one? Number 12. What's the answer? This 9 volt. Reading of the high resistance voltmeter is 7.5 across here. What's the current I? Yep.
Yeah, this is the R1, R2 formula again.
This one is simple circuit only.
Oh,
Just telling you the EMF formula, internal resistance. They don't draw for you. You have to imagine it's inside there. Right? V equals IR. Now you are looking across here. Find the current across here. You know that it's 7.5, so it's I times 15 ohm. Calculate your I is 0.5 ampere. That's all. Answer B. Yep. Can
IR.
can or not?
Oh, yeah, I can. Isn't EMF a different formula?
This one didn't derive. This one is the first part. EMF and resistance, internal resistance, that's all.
Oh, the not using EMF. Ah, okay, okay.
We are not using Kirchhoff's law yet.
Okay, okay.
We are just trying to test you, see whether you are ready or not.
Oh, all right, all right.
Right? Make sure you know how to define that. Right? Energy converted from chemical to electrical, because you told you are a cell per unit charge when charge flows through the cell or around a complete circuit. internal resistance of the cell causing voltage or energy loss in the cell. Right? All this must be in your head. Okay, this one apply Kirchhoff's law. The circuit of figure 5.1 shows two battery A and B and resistors are connected in series. Battery A has EMF of 3 volt, written for you. Internal resistance 0.1 ohm. Battery B has an EMF of 12 volt. Internal resistance of 0.2 ohm. Resistor R has a resistance of 3.3. Apply Kirchhoff's law to calculate the current in the circuit. What's your answer? Yep, can.
Wait, ah.
One positive
Wait,
answer.
I need to see the solution.
Say again.
I need to see the solution. I can't really do.
Okay. We have 12 volt greater than 3 volt, so we choose anti-clockwise, the current flow anti-clockwise. Taking direction of current as anti-clockwise. Right? Sum of EMF to the sum of IR. The sum of EMF, EB. Right? This one, we send the current to the clockwise, so we subtract. And I is passing through all these resistance. I, R, RB, RA, and put in your value. 12 minus 3, I, 0.1, 0.2, 3.3. Calculate out. Can
Wait, teacher, so how does this direction thing work?
we take anti-clockwise current. So this one is sending current out anti-clockwise. So it's 12 volt positive. This one is sending current anti-clockwise, so negative. Sorry, this one is sending current clockwise, so it's minus 3. Then
Oh,
the same current is flowing through all the resistance. Same current, right? 0.1, 0.2 is here, and 3.3 is here. And simplify it, use calculator. Can.
all right.
Calculate
Sure,
the
I
power.
can't find the.
I just send you.
Oh yeah, oh yeah, I got it.
Calculate the power transformed by the battery. Battery B. Can. You have calculated current,
E equals IV.
right? E times I, 12 times 2.5. We got 10 more minutes in case you get cut off. Okay, can.
Yep.
Our current we have already calculated, right? That's our current 2.5. Calculate the total energy loss per second in resistor R and internal resistance. What is the answer? Right? I square times the total resistance. No? Right? I is just now is we have calculated 2.5 square and add all the resistance out is 3.6 ohm. No? Can.
Which formula is this again?
This I square R. R is the total
Oh yeah,
resistance.
yeah, yeah. Okay, okay.
Any other comment? If not, let's carry on. The circuit of figure 3.5.1 may be used to store energy in a battery. Suggest how your answer in B support this statement. What's your answer in B? Ken? The circuit of figure 5.1 may be used to store energy in battery A. Here's a battery A. Suggest how answers in B support this statement. Basically, you're charging up battery A. Right? Power supply from B is greater than energy loss per second in the circuit. So energy is stored in battery A. Okay. We are charging up battery A. That's why energy is stored in the battery A.
Oh, because B has more power, so
Ah,
it
more
charges
power, the
up
current is
battery
flowing.
B.
Current is flowing that way. So it's supplying energy to battery A. Okay or not?
Oh, okay. Yeah.
Okay, you should be able to draw that. Like that. That's all. Can I
Yep.
explain how the resistance of a lamp may be calculated from voltage from its IV characteristic? Yep. Explain how the resistance of the lamp may be calculated for any voltage from its IV characteristic.
Isn't it just VOI?
That's all. R equals VOI. Hence, to determine R, read the coordinates of V and I from the graph and calculate VI. Okay or not?
Yep.
Two filament lamps are connected first in series and then in parallel to a 12-volt power supply that has negligible internal resistance. The circuit are shown in figure 5.2 and 5.3. Right? That one, respectively. State and explain why the resistance of each lamp when they are connected in series is different from the resistance of each lamp when they are connected in parallel. Yep.
Uh, is it like the parallel takes lesser? Eh,
Each lamp is connected in parallel has a greater PD than the lamp in series. This one is share this voltage across it. 12 volt share between these. This one is 12 volt, 12 volt. Resistance of lamp in parallel would thus be greater. Okay,
greater potential difference. Okay.
each lamp connected in parallel has a greater PD than the lamp in series. Resistance of the lamp in parallel would thus be greater. These two lamps share 12 volt, so each of them will be 6 volt, 6 volt. Oh. So when you calculate the resistance will be lower. Whereas this one, the 12 volt is across each lamp, so the resistance is the same. So it will be greater.
Oh, which one require more energy? Like to light up.
Uh, this one will be brighter, lor. This one will be less bright, lor. Because it is 6 volt only, 6 volt across it. This one is 12 volt across it.
Oh, so the barrel one needs more energy supply, right?
It has
More
more
power supply,
resistance
right?
because it has an operating voltage of 12 volt across it. 12 volt across it. So the resistance will be higher. Lor. Okay.
Yep.
This one will be asking you. Each lamp is marked with a rating 12 volt, 50 watt. Calculate the total resistance of the circuit for two lamps connected such that each lamp uses this power. You should be able to do that.
I square R.
Hmm. You want to calculate the total resistance. So it's you are given P power. You are given 12 volt. Can
50 over 12.
this is a case of lamp connected in
1.1.
parallel. Parallel is just your R is V square over R over P. So 12 square over 50 is 2.88 ohm.
Wait, sure.
Yep.
I thought the formula is P equals to IV.
Say again.
I
Say again.
use I use P equals to IV.
P equals to IV. For calculating which one?
To find the current. Oh, okay, sorry. Oh yeah, they're looking for resistance.
They ask you to calculate the total resistance of the circuit for the two lamps connected such that each lamp uses this power.
Oh yeah, that I also can, yeah.
So this is a parallel circuit, not a series circuit. Right? So total resistance, they are in
Okay.
parallel. So you divide by 2. They are identical. This is the resistance of each lamp. So they are in parallel, so you divide by 2. Okay, now. Yep. What's the problem? You
So
will
they
count